The investigation into the San Andreas Fault is trying to predict when and where its next major earthquake will strike. So far, the only certain prediction is the far distant future of the San Andreas. Look 20 million years ahead. If the plate movements continue to follow their pattern, Los Angeles will end up becoming a suburb of San Francisco. But predictions on a shorter time scale are more difficult.
If you were to ask the question, can we predict earthquakes? My answer would be no, because I know what your question really meant is, can we predict that an earthquake is going to occur on a certain fault at a certain time that we can specify in the future? And we cannot do that. But there are many things we can predict. We can predict which faults are likely to produce the big earthquakes. We can predict how big the earthquakes are likely to be. And we can even predict the probability of the earthquake occurrence over some period of several decades.
Predictions are most crucial where the San Andreas runs to the south of LA. Here in the Coachella Valley Desert, geological evidence of earthquakes stretches back 1,500 years and more. And they follow a regular pattern. Major earthquakes strike here with monotonous regularity every 200 years. But the latest one is long overdue. There hasn't been an earthquake here for more than 300 years. That's a concern because parts of the San Andreas Fault system run straight from here towards the city of Los Angeles. The faults will transmit earthquake shocks in a straight line towards California's biggest city. Geologist Yuri Fialko regularly monitors how the ground moves on either side of the fault line. He lines up his GPS equipment precisely over a series of metal pegs fixed into the ground.
This information is crucial for estimating how fast the fault slips at depths and what is the rate of accumulation of strain in the crust. In other words, how close the crust is brought to failure by slip of the fault at depths.
The repeated ultra-precise measurements reveal that land here on the surface hardly moves at all. This is a problem because deep underground, the stresses and strains are still building up.
The fault is moving at depths at a fairly high speed, and this deformation is growing and growing and growing with time.
Miles underground, the deep fault is moving at more than an inch a year, which tells Fialko that in the centuries since the last quake, the surface should have shifted 300 inches, 25 feet or more. But it hasn't. So sooner or later, something's got to give. And Fialko knows what that something will be. The rocks themselves.
And one example is this type of rock, which is called granite. This is in fact the rock out of which most of the Earth's crust is made.
A microscope reveals the crystalline structure of the granite. The crystals make the rocks tough, but they have a hidden weakness. The bonds between them may suddenly crack under stress.
Basically, once this material solidifies, it is able to crack and be sheared on the fault surface. And the brittle behavior of these rocks is what lies behind the physics of earthquakes.
Granite rocks underlie all of the San Andreas Fault, but right here, the rock's under greater stress than anywhere else because it's so many centuries since a major quake occurred.
And now we're over the 300-year limit, and so it means that the amount of strain that has been accumulated on the fault at this point is very close to the maximum strain that this fault has ever seen through its geologic record. And this is a fault that is capable of generating great destructive earthquakes.
Fialko believes the coming quake could be the big one that people have been talking about for years. And the effects could be horrific because of the population density of Southern California. When the last huge quake occurred 300 years ago, Los Angeles was just a tiny Spanish mission community with fewer than 100 people. Now it's America's second largest city, with almost 11 million people living in the earthquake-vulnerable metropolitan area.
People who live in California probably experience a small or a moderate-sized earthquake every year. A few things moving in your house, but it's really actually kind of fun. There is no major destruction. People just go on with their life. Much bigger events, on the other hand, are quite a bit different story.
Scientists have long known that earthquakes generate several distinct sets of waves. They travel at different speeds, each spreading damage and destruction out from the epicenter. Modern city buildings in earthquake-prone areas like California are engineered to cope with such waves. Now, new research by geophysicist Professor Andreas suggests that the San Andreas may offer a new and even more deadly threat. Razakis researches how earthquakes rupture along straight-line faults, just like the San Andreas, where it approaches Los Angeles. He creates his own mini-earthquakes, representing the San Andreas fault by a hairline crack in a thick, transparent block. This special material shows up internal stress lines when it's lit by a laser. And the earthquake is triggered by a tiny explosion.
3, 2, 1, 0. The load has dropped, and the explosion was big enough that we even have a crack.
An ultra-high-speed camera capturing 10 million frames a second reveals a startling and newly discovered phenomenon. This frozen picture reveals stress lines speeding along the mini San Andreas in the milliseconds after the explosion. The cone to the left of this frame is a previously unrecognized type of shock wave racing along the rupture line from the earthquake's center. On a microscopic scale, it looks and moves exactly like the sonic boom produced when a supersonic aircraft such as Concorde breaks the sound barrier.
Because we also see Mach cones, lines that are emitted from the rupture tips as from the tips of moving aeroplanes.
And just like a sonic boom, it can be dangerous.
In the same sense that we hear the sonic boom from the Concorde, you're going to feel the sonic boom from the rupture.
The danger comes because many high-rises just aren't built to cope with extra stress from this newly discovered type of shock wave.
So if you are an old building, for example, you'll take one wave, you will accumulate some damage, and very soon after that, you will get very strong ground shaking because of other types of waves coming also.
The high-speed ruptures that Razakis calls supershear happen where faults run in a straight line, which might help explain a 100-year-old mystery surrounding the Great San Francisco Quake, the natural disaster which launched the entire San Andreas investigation. The overwhelming damage in San Francisco has long seemed surprisingly out of proportion to the 7.8 magnitude of the quake. And there's a particularly straight section of the San Andreas approaching San Francisco. So many scientists now believe that the damage was greater than expected because the 1906 quake had traveled at supershear speed. Of greater concern to modern emergency services is not what happened a century ago, but what could happen tomorrow. Because there is a similar straight section of faulted ground heading straight towards Los Angeles. And if a super shear earthquake develops on that line, then the consequences could be disastrous. All of the investigation's warnings about the San Andreas came together in the fall of 2008 with the biggest earthquake drill ever held in California.
If this earthquake would have happened in reality, there would have been buildings coming down. We know that there would be no water now in certain areas. So that's what this exercise is all about.
But what are the real chances of Los Angeles soon being hit by a massive earthquake? Frighteningly, the best scientific consensus now warns that there's a 99% chance of a major quake in Southern California within the next 30 years. To better understand the threat to LA, the geologists produced their study jointly with experts in charge of the city's disaster planning. And none of them doubt that the big quake is coming. This specter of disaster to California's people and cities motivates the search to unravel the secrets of the San Andreas Fault. All the evidence is finally in. The damage reports from the 1906 disaster show the fault's 800-mile path. The different types of rock at Muscle Rock provide clues to how the fault was created 20 million years ago. The river bends prove how fast the land is moving. The mineral talc explains why some parts slip without major quakes. The brittle granite rocks reveal a threat to Los Angeles. And recent lab experiments uncover new and more dangerous earthquake shock waves. But one goal has eluded the rock detectives who study the greatest fault line on Earth. When will the sleeping San Andreas come to life once again? It could be any time. The investigation into New York City's geological history begins here, with Manhattan's rocky outcrops. These rocks are clues to how the land was made and how its geology helped it become a dense, thriving, pulsating city. They're scattered all over Manhattan, poking through the surface of parks and through the concrete between the buildings. Some, squashed between two apartment blocks, are the size of a whale. They are the extraordinary survivors of ancient times. Most importantly, they are the surface tips of the bedrock in which Manhattan's buildings are anchored. Gigantic skyscrapers stand in two clusters, in downtown and midtown. In the section between, the buildings are lower. The clues to the shape of Manhattan's familiar skyline are the rocks beneath the surface. A leading expert on the rocks in New York is geologist Charles Megarian.
The entire history of the development of the Earth's crust is emblazoned in the rocks beneath us. The rocks here in New York City harbor an ancestry that dates back over 1 billion years of time.
Megarian is searching for evidence to show how the city's bedrock was made. At Inwood Hill Park in Upper Manhattan, he's found an extremely hard piece of the bedrock known as Manhattan schist. To the untrained eye, it's just a piece of rock. But to Megarian, this is his first clue.
The rocks that we're looking at right here are rocks of the Manhattan Schist Formation. And these rocks are very severely deformed. And the structures here in this rock is a structure that comes up like this, bends around, and comes back down on itself as such. And in three-dimensional view, it's a structure that looks something like this, a very, very tight fold with a plunge towards the south here. These are rocks that were very, very strongly deformed over protracted periods of time. And it's the same bedrock that occurs over much of New York City.
This tight fold in the rock suggests New York's bedrock was formed under great pressure. To confirm this hunch, Megarian takes a sample to the lab for detailed analysis. Radiometric dating proves this rock is about 450 million years old. But the rock has even greater secrets to tell. It contains a kaleidoscope of minerals, which opens a window into the ancient world.
To me, minerals are like the instrument cluster in your car. They tell you everything about how your car is running.
Megarian uses a microscope with polarized light to view the minerals.
The examination tells us the former depth regime, how deep the rocks were. They tell you the age of the rocks. They tell you everything you want to know about the development of the Earth's crust.
What's striking about these samples is that the minerals inside are elongated. It is a clue that these rocks must once have been crushed by massive forces. And the colors support this theory. Under the polarized light, the sample from Inwood Hill Park shows up blue. This comes from a mineral called kyanite, which forms at great depths. It's conclusive evidence that this rock was compressed deep under the surface. Rocks forged at these depths are much harder, ideal for a city's foundations. But what gigantic weight was on top? Megarian believes there is only one answer. The rock was once buried under the crushing weight of a chain of massive mountains.
The minerals that we find in the bedrock units of New York City tell us that the rocks of New York City were formerly buried when they were formed under very high pressures, and that those high pressures indicate that these rocks formerly were produced at depths of 20 to 25 miles, and probably the mountains were as high as the Alps are today.
But even the most impressive mountain chains can't survive the ravages of time. The Rocky Mountains, for example. Millions of years ago, they soared nearly 6 miles into the sky. Today, erosion has halved their size. The same process happened in New York. Rain, wind, and ice wore the ancient mountains almost flat. But the microscopic crystals found in the rock in Manhattan testify that they existed in the past. How did the mountains form? The answer lies in the way the Earth's crust moves. A network of interlocking individual pieces makes up the Earth's surface. Geologists call them tectonic plates. Over millions of years, they collide and break apart to form different continents. 450 million years ago, the Earth's surface looked completely different. North America was much further to the south.
North America was tilted 90 degrees clockwise from its present orientation, and it was straddling the equator. As such, the climate was tropical. The east coast of North America was really experiencing Club Med conditions.
The weather may have been awesome, but the ancient East Coast was heading for trouble. The plate beneath it was moving. The East Coast was on a collision course with ancient West Africa. 450 million years ago, they collided. The impact unleashed geological chaos. Under intense compression, the land was forced upwards to form a soaring range of mountains.
The collision that took place is the most fundamental and impressive mountain building event to affect the east coast of North America.
Today, all that remains are their stumps. Stumps that form the bedrock of modern-day New York. The collision that built up the ancient mountains also folded the bedrock into dips and rises. These folds are responsible for the shape of Manhattan's skyline. The city boasts 2 clusters of skyscrapers in downtown and midtown. Here, the hard bedrock that formed deep underground was forced up. It is now close to the surface and provides solid anchorage for the high-rise buildings. In the dip in the middle, the rock was folded down. The area is filled with loose sediments, less suitable for skyscrapers.
When the bedrock is at the Earth's surface where it's actually exposed, then it's pretty easy to build tall buildings because you can root them directly into solid rock. However, In areas where the bedrock is deep and covered by glacial sediment, in those cases, it's very difficult to build tall buildings because you need to root those buildings either into solid rock or build concrete abutments called caissons that can support tall buildings.